Okay, so we learned that the proven model can be implemented in a similar way to the regression model. I will skip this page. And like when you have two regressors, also you can predict the probability of denial in a similar way. Just first calculate the linear z-value and then plug that into the standard normal distribution. Then you will get the probability. And now to check the statistical significance, the idea was the same. The coefficient is 0.71, standard error is 0.08. If you calculate their ratio, the coefficient estimate is 8.51 times larger than 8.5 times larger than the standard error, so which is statistically significant, or p-value is 0. It's exactly same as the t-stat rationale. And also you may now let's calculate the different denial probability between black and non-black. So if black variable takes 1 and the pi ratio is fixed at 0.3, then if black, the denial probability is 23%, but if non-black, it's 7.5%. So the difference in the rejection probabilities is 15.8 percentage point. So here, of course, it may still have omitted variable bias in the same logic as before, but we are going to ignore omitted variable bias right now. So what's more important, and what I want you to focus on here is, so we did the same thing earlier. Let's compare. Where did we do that? So here, we compared non-black applicants to white applicants, and when you calculate the probability of denial, the difference was 17.7 percent point. 17.7 is this coefficient, right? So that is what this coefficient means. This is the difference between black and non-black. But now let's go back to the proven model. The difference is 15.8 percent point, but the coefficient is 71%. Doesn't make sense. So this is important. Now, as I said, the coefficient cannot be interpreted as the difference in probability. It only means that being black increases the score by 0.71 points. But score has no real substance, so means nothing. And now we will study what's going on in this nonlinear model. So let's think about, I think the textbook does not have enough explanation on the nonlinearity. I don't know why. Overall I like the textbook a lot, but I don't like this chapter. I realize it now. So I made up my own slide. So what I did here is I first ignore black variable. So I will use this result. I copied these numbers and only using pi ratio, let's predict. So I considered 5 different pi ratios: 10%, 30%, 50%, 70%, 90%. And first I calculated their z-value, the score, using the estimated coefficients. So it's easy. We have the result table. So calculate the z-value, and z-value increases as pi ratio increases because the coefficient was positive. And from the z-value, using the standard normal distribution, I calculated the denial probability, the predicted denial probability. So if your PI ratio is 0.1, then you are going to be denied with 2.89%. And if your PI ratio is 30%, you will be denied with 9.62%. And like 50%, 70%, 90%. So denial probability is calculated. And then finally, I calculate their difference, the increment, but how much probability increases in each interval. So then, now what you can see from here, there is a clear pattern. First, z-value, so PI ratio increases by 20% point, 20, 20, 20, 20, and then z-value also increases uniformly, equally. The increments are equal all over the 5 intervals. So this is obvious because z-value is calculated linearly. Z-value is a linear function of PI ratio. So that's the definition of a linear function. When x increases 1 unit, the outcome z-value increases always by the same amount, as much as the slope. So that's linearity. However, from this to this, calculating the standard normal distribution probability is not linear. That's the problem. The nonlinearity arises this point, this step. So there, as a result, the probability increment, the increment in the probability is increasing. So first 20% increase in PI ratio increases the denial probability by about, say, 7% point, and then 14% point, and then 21% point, and then to about 23% point. So as you see, probability increment was small and then it goes up. It is because the probability function looks like this. The probability function looks like this, so it is not linear. It arises because the probability curve is nonlinear, and in this case, in the probability model and in almost any probability distribution used in this analysis, the curve is, as you see, it is s squared. So it goes like this, and then so you're like flip. So it goes like this. So it's flat here, and then it becomes steeper, and then flatter. So it's flat at the beginning and at the end, near 0% and near 100%. But it is steeper in the middle, so near 50%. So as you can see, so near 50%, the increment is the biggest. But as the probability goes to the extreme, then the increment is smaller. So exactly this is what I said. So the change in the PI ratio is the same, but as you go to the extreme, the same change causes only small difference in the final probability. So as I said before, going from 50% to 51% is not that difficult, but going from 99% to 100% will be super difficult. So that same intuition holds here. So this nonlinearity is a unique aspect, unique feature of the probability model, the difference from the linear probability model. So then we may characterize the nonlinearity using mathematics. Simple. So remember, the probability model explains the conditional probability of y given x. So given your PI ratio and other variables, what is your probability of being denied? So we fit this probability onto this functional form. Standard normal distribution, and inside is a z-value, linear z-value, right? And what we are doing here is we are looking at the effect of x on this probability in the end, right? That is what we did here. So that if you make the difference in pi ratio extremely small, it becomes a differentiation. So if you use the chain rule in the calculus, the slope is calculated. So differentiation, if you differentiate this function with respect to x, you have to differentiate the function inside and then function outside and multiply them, right? Because it's a composite function. You have this. The nonlinearity is obviously coming from this. The coefficient is always constant. So beta 1, the effect of beta 1 is this step. So the change in pi ratio causes a change in z value as much as beta 1. And then from z value to probability is this. So this is step 1, this is step 2. Step 2 has nonlinear function. So it depends. If you change x, this derivative will be different. As I said, it's flat, steep, then flat. So this is the source of the nonlinearity. So increment is not constant. That's a simple mathematical illustration of the nonlinearity. And also, we may now then so that was the key difference between the linear probability model and the probit model. And then it causes a big difference. It's a critical difference, especially in interpretation and comparison. So in the earlier slides, the linear probability model using pi ratio without black, so single regressor case, had a coefficient of 0.604 in the linear probability model. But in the probit model, the coefficient was 2.968. The problem here is there is too big a difference. Why are they so much different? It's a big problem. Like earlier, I could explain this. If your pi ratio increases by 1 unit, the probability of denial increases by 0.6, like 60% point. That was interpretation for the linear probability model. But what about probability? That is different. Linear probability model coefficient was effect of x on y probability, on y's probability, but probit coefficient is not capturing the effect on the probability. This is the major difference. Probit coefficient only captures the effect on the imaginary score, which does not exist in reality. So they are not comparable. It is purely imaginary scale. It has no meaning, but the only exception is its sign. So their signs are always the same, will be always the same. So if the probit coefficient is positive, usually linear probability model will be also positive. So positive means pi increase in pi ratio, it will increase the probability of denial. That's the only possible interpretation from this result and statistical significance. However, then how can we make them comparable? So we would like to make the probit coefficient comparable to the linear probability model's coefficient, and the answer is also calculate the effect on the probability. The score z value is not a common object. It does not exist. So have some substantial effect on something that exists, which is the probability. It is interpretable object. And we know this derivative is calculated this way, and we obtained it earlier. And this is nonlinear, so you have to calculate this one. So this is probit model coefficient. Probit model coefficient must be multiplied by something else. to have a meaning. So this is nonlinear, and when you multiply them, we call this the marginal effect. So it's not only coefficient, but it's an effect on probability. So we call this marginal effect because we obtained it by differentiation, marginal. Therefore, now it is now both the marginal effect and linear probability coefficient are both effect on the probability, so they are now comparable. So as you can see, this nonlinear component is the difference between linear probability model and the probability coefficient. So the marginal effect and the coefficient differ by this much, which you have to consider in comparing the results. Okay, this is it. This is all I prepared for today. And summary. So summary, simply when you interpret probability coefficient, first, there is no economic meaning. You may interpret its sign, you may interpret its statistical significance, but otherwise there is no meaning. Second, the marginal effect is a separate or different measure, more important measure, more meaningful, and it is calculated as the coefficient times some nonlinear derivative. So you don't need to memorize what is the derivative. It will be calculated by Stata automatically, so don't worry. But you have to add some additional lines, programming. And third, the marginal effect is different at different points. It is flat and then steep and then flat. So the derivative will be different at different points. So all of these problems and features are coming from the nonlinear nature of the regression model. And the nonlinear nature of the model is arising from the special structure in the dependent variable model, dependent variable, which is being binary. So because it is either 0 or 1, we have to think about the probability, not the direct outcome. So probability always between 0 and 1, so linear model does not work. So we have to consider nonlinear model. So you need to consider marginal effect and different marginal effects at different points. Okay, so we will continue this chapter in the next lecture. See you later. Bye.